Right, we are live. Hope everybody's having a good day. Hope it's going well in your side of the world, wherever you are. Um, Doing it from the truck today. So we're out and about, got stuff going on. No whiteboard again this time. Honestly, it seemed like this went pretty well the last training we had. So we got a lot going on. It's summer. You know, it's something I'll give everybody a second to log in here. Be careful, please. It is summer. It's hot. It's difficult. This is a very challenging time of year, no matter what we do. So just be thinking about yourself, be thinking about your teammate, who you're working with, working around. Make sure you're looking after them. I do have an example pulled up on the screen here. So we're going to go through a scenario that we recently had. I've already talked to the technician about this, and this isn't fully resolved, but I want to discuss it because it's a pretty good case study. And then I've got another troubleshooting example we'll get into after we talk about this. But this one brings up some unique scenarios. And what I've got posted on the top there is this is the report that came in. So this is what dispatch took down and what we had to go off of when we went on site. So we'll go ahead and start diving into it. This building has a roof with multiple carrier. It's not this exact series. This is just a real quick. I had to kind of slam this together last minute, but basically a large commercial carrier. This is an older one, I believe. This one here on the screen is technically a little newer. Anyway, aside from that, so the call was RTU3 was down, possible airflow issue. That was what they believed. Both circuits are tripping on low refrigerant. They had low saturation, low supply fan, or supply fan ramps up and then drops back down at startup. So this is the call that comes in. And the reason they were considering a possible airflow issue was when they first went up to inspect the unit, the on-site engineers, they they found the low refrigerant or the low pressure alarm on the touchpad. And then they went around and they checked the blower fan, and the fan was the whole fan deck was really cold. Now the system had shut off at this point, and from what I understand, I don't believe when they got to it the fans were actually running at that time. But I don't think it was. I don't know if they power cycled it or what. Either way, their feedback was, well, it was really cold in the supply cabinet, and so um, because of that, he really believes that that may be an evidence of a fan issue. So dealing with low saturation. So the technician gets there. Uh, he's looking into it. He sees the supply fan ramp up, and it ramps to like 2 inches of static, and then it comes back down. Now this obviously does have a VFD in it. Part of that process, it was a little challenging seeing that supply fan do that and trying to understand, okay, what is happening that's causing me to spike that high on static and then come back down. But he said once it ramped down, it stopped at around 40 hertz was where it leveled off at from what he could tell. But if I understood him correctly, it was still fluctuating a little bit on the supply fan speed. Uh, so at that stage, though, he was hovering around 1 inch. He said 0.7 to 1 inches of static, and he needed to verify the circuits. So the first thing he did is he gauged up. I don't have his actual numbers or readings here, and I don't. We can do more of a deeper case study here. My point is not the actual diagnosis because one, we don't have one yet. My point here is I want to actually examine the workflow process. So once he gauged up, both circuits were doing something a little different. And one of the biggest things that stood out to him was the TXV seemed to be fluctuating quite heavily, which made him think that maybe circuit one specifically had some kind of TXV issue. And one of the decisions he made was, well, because the supply fan was fluctuating the way it was, he ended up locking the VFD off at 30 hertz so that he had a constant airstream. Um, but uh, and so with the constant airstream, he'd be able to get hopefully more stable readings. So I have a little bit of feedback with that. So as he was staging it up, he went, one compressor by itself, then he brought in a second compressor, let them both run together on circuit 1. Then he did the same test on circuit 2. And the final diagnosis, he's recommending that maybe the TXV be replaced on circuit 1 because of the heavy fluctuations. It was going from just a couple of degrees of saturation and then was spiking back up to I forget I think it was in the 20s, I believe. So as it was running, and then he had very similar results when he brought in the second compressor. And if I'm not mistaken, he was running low saturations throughout that whole duration. Because one of the first things he did when he got there was he powered the unit back up. I think that's what it was. It was down. He powered it up, and it ran fine for 30 minutes, and then tripped on the low saturation alarms that he was seeing. But when he did his testing on circuit 2, circuit 2 looked like it was possibly undercharged. So he was having low saturations, high superheats, thinking it may have a charge issue. Now, we weren't able to finish. This is an after hours call, by the way. So he wasn't able to finish all of this. He was able to get it to a basic point to where we've got eyes and we've got a good visibility onto what's happening. Now we can discuss it, come at it with a little bit better plan during hours, or try to find some way of getting this call addressed. Um, a couple of feedback points that really stood out to me was when you're doing something like this, him locking off the fan speed is perfectly fine. That is a valid troubleshooting exercise and just putting the VFD in hand. I don't recommend though running just a 30% or a hertz, 30%. I don't recommend running 30 hertz as your point. Obviously, we have to be mindful of our static pressure. We don't want to overshoot that pressure and end up causing any kind of damage or tripping a high static switch. But um, I would want to run that higher. So 40 hertz might be enough to run 2 compressors on the same circuit comfortably, but you're really probably looking at 45 to 50 hertz to get both compressors to stay on and stage together smoothly. So that's one of the things with 30 hertz, you're running at the drives is basically minimum speed. You really shouldn't see that drive get down to or below 30 hertz very much or very often. And typically the only time it's going to, or it should, is if there's a really low load scenario. Now, something that let me take a step back. One of the things that's really easy to do is get tunneled into a possible refrigerant issue. And we spend so much of our time, so much of our day trying to evaluate refrigerant circuits that it's easy to let that kind of take over the focus of what you're working on. So what I would encourage you to do is uh, spend more time making sure that the overall mechanical is sound and good. So when I walk up to a system and I begin to do any kind of troubleshooting, or when I begin to try to evaluate, okay, what do I do next? One of the last things that I do is hook up gauges at all. If the interface itself has pressure readings I can use to evaluate or anything like that, um, that I may reference those to a certain extent, but I won't actually include those into my primary troubleshooting process until I'm confident in the rest of the system. More specifically, in this particular application, the fan, something weird was happening with the fan on this RTU. It's the fact that we had a high load, it had been down, but when we came back to turn it on, it settled out at around 40 hertz with a high load and in a high ambient outside. Um, I don't know what his return air temperature was offhand, but it seems weird to me. Something is off about that. Why would we only be running 40 hertz out of 60? So, I would expect to run 60 hertz for quite a while. So what's restricting me downstream on the airflow side? Why are we having to ramp the fan down so much? Now, the fan running to a 60 hertz right out the gate and then backing down, that should be normal. The fan is going to ramp up to try to meet static set point. It's got a control pid on that speed that's going to do that. So I would expect that. That's fine. But I wouldn't uh, I wouldn't expect it to come back down that much. Maybe initially, it ramp up to 60, come back to 40, and then start coming back up to somewhere between 40, 50s, probably in the 50s, especially having been down and not been running. So that would have been one key indicator that I would have pointed out is um, that's a mechanical anomaly. Something weird is happening there. Now, those units use a static pressure sensor that's on the economizer side of the system, which in this particular case, you can see your condenser coils on the right-hand side of this picture, but over on the left-hand side is your economizer section, and the economizer board and the static pressure sensor he was looking for is on the back side of that section inside of there. Um, so I start questioning, is there possibly a static sensor issue? Do we need to get a manometer out? Do we need to verify what my actual static pressure is? Even if you lock it off um, at the uh, uh, at the drive. Let's say you set it at 30 hertz or set it at 40 hertz. Um, I need to verify that that static sensor is actually reading properly, which one way to do that is, okay, well, we have an interface on this system. Hopefully it works to some degree, but if you go to the pressures section under the air side inside of that carrier navigator, you'll get to the static pressure, the active static pressure. And so if you do lock that drive off at a certain hertz, you could just look at whatever that static pressure is, then go around and see with your you would have to unhook the static pressure sensor and then plug it into your manometer and see what the reading is, and let that help guide you as, okay, how close are we? If we're within a tenth of an inch, then you were probably fine. It's not a static sensor issue. What else is going on here? If we're more than that, if we're several tenths off, uh, something may be wrong. We that sensor or the board, the economizer board it's plugged into, I've had both happen. Could have an issue. I've had it where um, something got crossed. Now nobody had worked on this unit recently that we know of, but uh, yeah, I've had the sensors get crossed up before, and it caused some weird issues like that. Actually, specifically, I've had an issue where the sensors always read um, what was it, high? It was something along those lines. It was actually, no, it was the addressing. That's what it was. It was reading the wrong sensor. The dip switches for the economizer board was set to the wrong address type for the microcontroller in the panel, and it was reading the wrong sensor, and so it never would stage the fans up. That was a totally different job. Sorry. Anyway, um, yes, the static pressure. I feel like, and next time we go back here, I'm not going to commit to the TXV and the low charge diagnosis yet, because before he locked it off, uh, as it was running, if that fan, um, if that static pressure was fluctuating as much as I understood it was in talking to him, uh, then that's going to cause a heavy fluctuation on our static pressure. Or, I'm sorry, on our superheat and our TXV, because we got to keep in mind that in the sequence of things, your evaporator coil is at the mercy of the airstream. So whatever the airstream does, whatever the fan does, it is at the pure just mercy of what it decides. So we have to think about that. If we're seeing some weird fluctuation, which honestly it sounds like a hunting. So in a hunting scenario, the TXV is gonna fly way too far open. It's gonna flood the coil. It's gonna see that. It's gonna overreact. Then it's gonna come back and it's gonna underfeed the coil. So we see our superheat spike super hard. Then it comes back. Then it goes back. Now a sticking TXV where the rods in there are beginning to fail can cause a very similar condition. It'll almost look like hunting, even though it's truly not. It's the internal of the valve getting hung up as it's trying to actuate. So it can be very difficult to troubleshoot both sides of that. Now, what causes a true hunting valve is typically an oversized valve. If the valve can't match the capacity of the compressors or the circuit it took to, and it's too large, then that will cause that hunting it very aggressively, which we don't. That's not our case here. You know, all this is factory equipment. Um, so yes, my push here is the troubleshooting process to be mindful of what's going on and what's happening in our mechanical so that we don't end up trying to diagnose a refrigerant issue for a mechanical problem. And some of that does come to understanding. So he wasn't aware that 30 hertz was so detrimental to your heat load on the system. Now, if 30 hertz in that scenario, you know, given the context, if we were in the middle of winter, maybe a different story. We're in the middle of our summer. So 30 hertz, 40 hertz, we should rarely see those numbers on any of our supply fans. There's way too much load, especially for a system that's been down. So that's one of those indicators to help steer you on where do you go next and what's the next right step. um, there was another scenario. This wasn't the actual case, but in the early parts of the conversation something very interesting came up. So the first version of the story I heard was when the tech got there, and this was not from the tech, this was from a third party that was working with the tech remotely. But when the tech got there, he got the supply fan on. And then as soon as the compressors would kick in, the supply fan would turn off and the system would automatically go into a low pressure and trip out on the compressors on low pressure. And as soon as the compressors would turn back off, the uh, the fan would re-engage and spin back up and it'd come back up to speed. And it was doing that repetitively, and they really weren't sure what to do because the fan kept dropping out. Now, that was just a misunderstanding in actuality, but I want to challenge something like that is possible. You could have a real scenario where that was the case. The fan could run, but as soon as the compressor tried to kick in, the fan wouldn't run anymore. I would um, I would challenge your thought process. Okay, so what do you troubleshoot? Now, I'd love some feedback on this. You have that situation in front of you. What do you troubleshoot? How do you troubleshoot it? What are you going to do for that? You know, you can't run it, obviously. So it's clearly something's happening. Well, why would the fan drop out because the compressor kicked in? What are some possible outcomes? Like I said, let's get the chat going here. We've been fairly quiet today. I know I've been talking, kind of guiding through this story a lot. We're going to get to an actual troubleshoot example here momentarily, but I want to finish this thought process. So if you would just be patient with me, let's work through this. What are some possible things that would make a supply fan drop out when a compressor turns on? And we're getting electrical here. So we're starting to dive into more of the control side. Is there some kind of safety parameter that would make that happen? Is there some kind of dehumidification setting that might make it want to do that for some odd reason? You'll just something. What do you think might cause that? Let me see somebody. Throw something at me. Come on. Anybody got any ideas? Okay. I would venture to say it starts with we have to start thinking about the controls of a system. So one of the conversations I had this morning is we get to a place where we have to start thinking like a controls technician, like an automation tech, right? The only difference, though, between us as the mechanical service tech and an actual building automation tech who is writing these programs is we're working with a system that has a program that's already written, and we don't get to manipulate it the same way they would. So automation technician, he's working with a system that's considered a PLC, a programmable logic controller, and he gets to completely manipulate what that controller does. I mean, to an extent, there are limitations, but point is, he decides, and if something's not working, he can fix it. Where in our case, our control board is a locked down PLC. It is a device that the manufacturer writes their program for. And when we run into these type of scenarios where these things aren't lining up, we have to start thinking about what is the logic of the unit doing that would make it do this. Now, how do we find out what the logic is supposed to be doing? So the question is, what could cause our supply fan to drop out even every time a compressor tried to engage? And then when the compressor shuts back down, our supply fan comes back on a large RTU, or just, yeah, we'll stick with this application on like a large carrier RTU as an example. What are some possible things? Where would you start with that kind of troubleshoot? So if we um, if we don't have, so if you don't know what the logic is trying to do, that is where the manual comes into play. So the sequence of operations built into the manual, while it may not be 100% complete, it'll give you a really good idea, typically, what that unit is trying to control. Now, you got to think, it's some of those sequence of operations can be lengthy. They've got pages written in an entire section of the manual that describes every little step in that process of what it's trying to do: start up, shut down, static, this, that. So we have to think about, okay, what's a basic sequence of this unit? The one, we have to have a start from the building. Then we have to call our fan on and get that up. Well, the fan runs off of static pressure, so we need to make sure that we meet that static pressure and we can maintain that with our drive. Then once we see that we have our leaving air temperature is not high enough, or I'm sorry, cold enough, we've got a high leaving air, then it starts looking at how many compressors do I need to bring on, or let's start staging compressors on and bring that supply air back down, right? So this is the basic, super basic sequence here. But nowhere in that process is there anything that tells the fan, hey, my compressor turned on, turn the fan off. So that should be an indicator to you that it's probably not even a logic issue, not in the controller, but it becomes a relay logic issue. That's just a fancy way to say that we've probably got a contactor or a relay, something control-wise, not functioning properly. So the first thing I would want to do in a situation like that is go straight to the output relay that controls the supply fan that sends our start signal, in this case, to the drive. And I'd want to verify, when that fan turns off, does that signal actually drop out, like, completely? Do we lose our supply fan signal? If we do, then I would venture to say that something may have broke inside of that board. But if we don't, or if the signal gets very weak, but the output is still technically there, let's say that output is a 24-volt out, but so when it's just the supply fan running, we see that 24-volt out maintains 24 volts just fine. But then all of a sudden, when the contactor coil for the compressor gets engaged, that 24 volts drops down to 19 or 20. Well, that could be an indicator that we may have a transformer issue. Now, what that would do to us is the relay for the supply fan could be the weak point in that process. So the first thing we identify is the fan dropping in and out. We go to the output of the controller that runs that piece. We see, is our output what's actually changing, or is it at the relay itself? We see that we maintain the output. Let's say the output never drops, but our voltage does. Well, that could be a transformer issue. That could be a coil issue on the relay or the contactors. If we've got an old relay that's got a coil on it that's getting weak, but maybe the contactors aren't as dramatically affected by that coil or by that voltage, they can run down to that low of an input voltage when they're a good, fresh, strong coil. Then you could see the other coils in that circuit stay on, while that fan relay wouldn't. That could also be an indicator that we've got a weak transformer. So the transformer can't carry the load like it needs to. Maybe it did at one time, but it's not failed yet, but it's getting weak. And so as it loads up and more coils get put on that transformer, more stuff is applied to it, the voltage begins to drop more and more off of that transformer. And that leads to the weakest coil is going to drop out first. And that's where you can see like uh, tap around. That's where you can see like a chattering issue sometimes, where if you got a whole bank of contactors that everything's coming in and you've got an undersized transformer, it can cause they can cause a type of chattering. Yeah, so in that, like you said there in the comments, it doesn't matter the type of coil, whether we're talking a contactor coil, we're talking a relay coil, a cube relay, the little ice cube clear looking ones. Doesn't matter what the coil is, but they can have intermittent drops like this, and it comes back to the supply voltage. Anyway, I think we've spent enough time on it. My main point to all of that was just to kind of talk out some troubleshooting processes and how we can just take steps and start to evaluate that. Now, the second part of that with the fan dropping in and out was not actively happening in this particular case, but it could. It could, is my point. All right, so let me bring up our other example here. Back over here. Okay. So the call. Okay. The call came in as the AC is making a weird noise and it won't cool properly. It really struggles keeping the house, the space maintained. So we can see our readings here real quick. As y'all start to see this, let's get the chat rolling, get your input in here. So our outside air is 100 degrees. Return air in the space is 78. We have a supply air of 52 coming. This is just a regular split system. Nothing fancy going on here. We have a evaporator saturation of 28, evaporator superheat of 4, a condenser saturation of 115, liquid line subcooling of 15, and a discharge superheat of 15. So I see one for airflow. Okay, so what do you think our airflow is doing? Do you think it's too high, too low? Let's talk a little further about it. Does everybody agree with that? Are we thinking airflow? If it's not airflow, what else could it be? Could it be gee whiz, come on, words. oil logged? Could we have an oil logged evaporator? Could we have a low ambient condition possibly? Um, I do see, a high temp drop, low superheat. So superheat's 4, got a high temp across the uh, uh, return air to supply air is quite high. I see dirty coil coming in from James. Um, Low saturation, low superheat, high temp drop, low airflow, fan speed too low. Okay, so let's dive into. All right, so we think it's low airflow. What are some steps we can take to confirm it's an airflow issue? More than just we've taken refrigerant readings and we've got a strong suspicion it's an airflow issue. So what is our next steps? What do we do from here? How do we address that? Do we think do we go static drop across the evaporator? Do we go fan speed, go straight to that? Okay, so yeah, take static, check coil visibly. You look at the coil visibly, it's not the best coil you've ever seen in your life, but you've seen worse. Um, on the static readings, so let's say we take a external static, and in this particular case, we're running a point, say a 0.8 external static. So we have a 0.8 external static. Current fan current draw can tell you some things. Okay, so our RLA on the fan is 1 amp, and we're running half an amp. So we have a 0.8 external, half an amp. So we say, are you saying decrease the airflow as in we're moving too much air, or do we need to move? Do we have decreased airflow? Which, let's be a little more specific on that. Not doing no work. Yeah. Yeah. It's talking about the fan being low on amps. So, okay. So we have somewhat restricted airflow or fan too low speed. Okay. So we get in there, and let's say the fan was at a medium speed. We got a 3-tap fan. We're at medium speed, and we bump that speed up to high speed. To update your results at that point, I didn't have one prepared for that, a different slide, but I'll write them down, make sure I keep track. So we bump it to high speed fan. We start pushing 30 on our sat. We get a superheat of 5. Our supply or return stays the same, but our supply goes up to 54, we'll say. And the discharge, superheat, and the liquid line subcooling remain the same. So all we really changed was we bumped up saturation a little. Our superheat came up a little, but our supply air also came up a little, but nothing else really was affected in that process. What restricted airflow or too low a fan speed? The high speed should raise your superheat and lower your delta. Yep. Damper opens 50. I'm not tracking with you on that one. Um, we don't have any dampers other than just maybe some balancing dampers. Okay, let's chase that. All right, so we're thinking uh, that maybe we have a damper issue. Maybe the balancing dampers were closed. Maybe one of them got shut at some point. So that's a good check. We need to do that. So you walk around the supply and you look at all your balancing dampers. Everything looks to be open. Nothing is significantly restricted. If any of them are closed at all, it's just slightly. Then you take a walk around the space, and you're looking at the actual registers. So let's just say they had ceiling registers. All the ceiling registers are open. Nothing's plugged up. Nothing's in front of any of them. Everything's flowing. Reminder, we have a point. So our static, external static went from 0.8, by the way. So when we went to high fan speed, went from 0.8 to 0.9. I'm going to say 0.8 to 0.9. So we increased external static as well. So what are we thinking? What are we thinking? So what do you check next? Filter? We want to go filter on it. So you check the filter. It's got a 1-inch pleated. It's not dirty, but it's not clean. So pull the filter out. Readings aren't affected. Very, very marginal. Not enough to document. Restricted supply. Okay, so we have a restricted supply. Well, we checked the dampers. We checked the registers in the space. So what else do we think? Maybe some insulation inside of some ductwork collapsed or fell. Is that what you're possibly thinking? Okay, so let's say we did a full supply duct eval, including dampers and the whole process. In that, we could not identify an immediate issue on the supply side. I would also venture to argue, even if we did have a restriction in our supply, would our external static still be that high? If we're, because you got to think, well, where are we taking our static readings? We're taking it, say again, we're talking regular split system air handler here. Say it's a little 5-ton, so pre-filter static, and right there at the duct, and we're taking a post unit supply right there as we're coming out of the supply trunk. So those two statics gives us our external static. Bypassing evaporator. Okay, so in that particular case, so let's say that one of two options could be maybe the evaporator, maybe a bracket rusted out on the evaporator, and it allowed the evaporator to sag because of an old rusty bracket, and so now we're bypassing around the coil. Okay. Second alternative would be the cover plates on the end part of the evaporator. This particular one, maybe it's just in a really old system, or rusted out so bad that it allows the air to go around it. You know, maybe the screw, maybe you had a couple of screws, or vibration. There we go. Maybe the vibration of the unit, maybe it's got a fan balance issue, and it caused the geez, caused the screw to back out of it enough to allow that flapper plate, that cover plate, to allow air to bypass. That could be a real alternative. To both of those, we checked it. Okay, so you take off the evaporator panel. So obviously we've shut the system down at this point. So we take it off. We inspect the evaporator coil. It's mounted properly, no major issues, no major flap issues. So as far as you can tell, without just tearing the whole thing apart, the evaporator is not bypassing in any way. Now, another way we could verify the bypassing is uh, our external static. So would we have that high of an external static if we were bypassing our coil and just flowing around it? Because wouldn't that remove restriction, which would ultimately lower our external static? Just something to think on. Let's see. Obviously the TXV, I agree. TXV issue, trash it out. We're gonna scrap the whole system. Yeah, I agree. They need a new unit. That would actually fix this problem. That would. You know what's terrible about that is it would. You could change out the whole system, sell them a new one, and this problem would go away. Uh, if you need more clues, hopefully that'll give you something. Okay. Um, Humidifier bypass. Oh, okay. So yeah, some of you northern boys are in here. We don't have a humidifier system on this. Yeah, no humidifier. I'm gonna go for the easy, inefficient compressor. Okay. So I chuckle, but in all actuality, let's talk about that. That is something that comes up frequently. We can rule out inefficient compressor for a couple of reasons. Yeah, I know you may mean it as a joke, but taking it in a serious sense. Um, the evaporator saturation, the fact that it's low, and the fact that our condenser saturation is adequate, it's 15 above of ambient, so it's perfectly fine. And the fact those two are there would be a hard indicator that that compressor is pumping. We're moving refrigerant through the system. Uh, so if that was part of your question, well, maybe that's why I can't get my system to look right, because I'm not pumping properly. You're moving refrigerant here. You can tell, if you were not moving refrigerant properly, you'd have high saturations, you'd have high superheats, you'd have low condenser saturations, your subcooling would be off, you'd have very different readings, and your discharge superheat wouldn't be so low. So an inefficient compressor is going to run wild with discharge superheat. In this particular case, if anything, we've got a fairly low discharge superheat at only 15 degrees. Usually somebody asks, I'll go ahead and restate. Discharge superheat is the difference between the condenser saturation, and if you want to get real specific, your discharge saturation coming out of the compressor, and you want to take a temperature reading on the discharge line about 6 inches off the compressor. That temperature reading from your saturation gives you discharge superheat. Let's see, low indoor airflow. Yes. So I think we agree at this stage. Low indoor airflow. That's a appropriate assumption. Now the question is, okay, we have low indoor airflow. Good for you. Now what? Right. So now we need to provide a diagnosis on how do we fix this? How do we fix our airflow issue? Sounding like an improper mounted TXV bulb. Okay. That's an interesting one. Let's work through that. Improperly mounted TXV bulb. So in this particular case, the bulb cannot read the suction line properly. So what's going to happen? Um, if you're not reading suction properly, then it's going to read the ambient air moving around it. So let's say our ambient air around the bulb is around 52 degrees. Um, so that's going to cause us to, if the TXV is shooting for, so let's say, a 12-degree superheat, 12 to 15, we'll use that as our example. Then we're going to see the saturation increase in superheat. No, we're going to see saturation decrease, but superheat is going to increase. Here, I got to see if I can do this live. Talk this out through my head now. Because we're not gonna see the temperature of the pipe fluctuate properly, and we're gonna settle out at our air temp. So our bulb temp is gonna stay. So basically means your pipe temp is gonna stay at 52 degrees, give or take. It's gonna have some fluctuation as the air fluctuates, but the saturation is going to try to track at 15 to 20 degrees below that. So that would mean our at 52 math. I got to do math. Let's go with 12. I can do that. That's 50, 40. So we're sitting at about 40. So somewhere probably between in the mid 30s to 40s on saturation, if everything equalized properly. So I think our issue there is we could rule out the bulb issue. Now we could do an inspection. We look at it, we're fine with that. But in just using our readings, um, we're running a low our superheat and our saturation are too low for what I would expect to see with an improperly mounted bulb. Yeah, math is hard. I appreciate it. I was not a math whiz. I tell you, we've got a guy on the team. Everybody knows who I'm talking about. He is a math whiz, and I call him for my calculator. Actually, I see him in the chat. Would you look at that? Span fitting the correct way. That's actually a good one. We look at it. So how about this? Now, this may be hard to articulate via chat. Can somebody explain the how to tell if it's spinning the right way? So what is the right direction for a fan to spin? How do you know just by looking at it without having any other uh, means of measurement? How do you know just by looking at it if the fan's going the right way? Anybody want to take a swing at it? I'll give you a couple of seconds. I'll explain it here. I'm just curious if somebody can articulate it via their words and uh, the curve of the blades. Yep, yep. So you're looking at the curvature. So the of the louvers. So that's it. That's essentially it. So it's going to come down to your louvers are going to cup paper towels. Yes, paper towels. That is the most effective method. Your louvers are going to cup, and your louvers are basically, you can think of it as throwing the air. So as they cup and say this hands the air, it's going to slap it and sling it by, and those louvers should be slapping that air and pushing it to the outlet side um, of the squirrel cage. So your cage has kind of this weird six type shape in it, to where it's got an output on one side and it's just got a big bulb on the rest of it, right? Well, those louvers should be spinning in that direction. So if your rotation is causing the air to hit the backside of that curvature, then your fan is in a reversed rotation. So this particular case, that actually is a pretty good thing to verify. Um, and I would say that we've verified that our um, uh, we verified that our fan is spinning the right way. We're not spinning in reverse. Now we could always reverse the fan if we were ever curious about it. Now, how would you do that? And you start talking. I'm pushing time here, so I'm trying to hurry. Uh, if our fan was reverse speed, but we've got a single direction fan, I mean, it doesn't have like a condenser fan where you can just flip two wires. That doesn't exist on this motor. Um, so then what? What are we talking about? Um, we're talking about uh, yes, we're talking a squirrel cage. So we're looking at the capacitor. So if you, on a single phase motor, if you switch the run and start legs at the capacitor, you will reverse phase on a single phase motor. So that's something to always verify for. And that happens. I can't tell you how many calls I've ran, whether it be condenser fan motors or blower fans, where that happened. They got the two wires mixed up, and our L2 leg was wired to our start leg, and our run leg was coming in on the other side of the capacitor. Um, yeah, it happens. Okay. Let's see. Undersized choking unit cause high static. Undersized return. Okay, so it could be an undersized return. That is possible. Mounted TXV bulb. At a proper RPM. At this stage, we've chased through a lot of examples, a lot of scenarios. The coil doesn't look that bad. It really doesn't. But when we actually go and take a drop across that coil, we see that it's got an excessive drop just for the coil. Now that can be really difficult because a lot of manufacturers don't give you just the coil's drop data. They give you the external static data, but not the coil drop, unless you're working on a furnace. But ultimately, um, in this scenario, we can only take it so far. At some point, we need to consider the evaporator as being dirty. Now, it got brought up a couple of times. Is the evaporator dirty? And my answer to that is it doesn't look that bad visually. But what you don't realize is how much is impacted into this particular coil. And it's not surface uh, level stuff. It's actually internal. So this particular scenario is a evaporator that's impacted internally through various forms of organic growth, as we say, um, without actually showing a whole lot of external signs. And this is a pretty common scenario to run into where the coil itself just it doesn't look that bad. You wouldn't think the coil would be that big of an issue, but once you actually get in there and start addressing it, you learn that it is. So at that stage, if you have the ability, if it's a scenario where you can pull the coil and clean it, great. A lot of times we don't have that luxury. So I personally, I don't like using chemical cleaners on coils, period. We as a team, we will not do that in general unless it is an extremely specific scenario. And if a customer requests a chemical be used on a coil, we will not honor any kind of warranty against that coil if it fails at some point shortly after us doing that. It's just I've had way too many issues with that process. Um, Now, if uh, uh, if in this particular case, though, something that I am okay with doing on occasion is Viper, where your refrigeration technologies has a aerosol style can of coil cleaner. Now it claims no rinse. Personally, I still rinse it with like a little pump up sprayer or something. But I've had good results with those before and getting a real long bristled brush, a stiff bristle from Home Depot or something, and trying to brush out, or you can get those refrigeration coil brushes. They work really well too. Little brown, they're brown or blue. You can get them both ways, a little white handle. Anyway, trying to brush that coil out and just flush it. Another thing I've done to just get it functioning. So in this particular case, I would have expected to see that our evaporator would have been icing over 28 degrees. This thing would have taken a few hours to ice over, but a couple of times a day, it would have lost control of the house or the space, and it would not have been able to maintain the load fully. So 28 is enough to do that. Above 28, so above 30 degrees, 30 to 32, you might not even ever ice over. You're right there at a tipping point where it's not quite cold enough to get a hard freeze on the coil unless it actually ran for all day and nonstop. Then you might actually like have a icing issue. But at 28, you'll start to see that. And running a 4-degree superheat at a 28 saturation, those two things together, that coil is going to ice fairly quickly. It's got a lot of good refrigerant in there at a really cold temperature. That liquid that's just sitting through that whole coil boiling off in there is gonna cause a lot of icing pretty rapidly. Um, so that would be my expectation here. So coming in, and we just need to, we can't pull the coil today. We got to clean this thing regardless. Hot water. One of my favorite tricks is getting a cup, and not even my pump up sprayer, but getting a cup of hot water. Get as hot as whatever they have on site, and heavily soaking that coil in just hot water, and letting some of that just growth and whatever is on there try to seep out of that coil. It's hard when you get a coil that's impacted. It's actually internal to the coil to get that to flush back out of there without pulling it and without getting some kind of actual pressure on it. A pump up sprayer can help. If you can put hot water in your pump up sprayer, a lot of them don't do well with that. At the same time, by the time the water gets all the way through the pump and then sprays onto the coil, it ends up uh, it ends up cooling off enough to where you lose the effect of the hot water. It may be quite warm water by the time it's coming out of your sprayer, but it's not hot. And my objective here is I want legitimate hot water hitting that coil. Um, to try to just flush some of that out. And I've had really good success with that where um, if if you take that hot water and do that process, not even using cleaner, just the hot water and a long bristled brush, and you'll have to flush the drain pan out as you go because you'll start to see it build up in there. If you just do that and be patient with it, you can get a coil that's it's at a tipping point. It's not a hardcore, this thing won't run at all. So you could probably get this thing to where it'll maintain above, in the mid 30s saturation, and that may get them far enough to where you can schedule to come back and properly treat that coil at a later date or something. And at minimum, just keep them running to where when you leave, um, you don't have to leave them just completely down. We can do something to get them a little further, get some of that trash out of there. Anyway, we go through the process. Let's say we do that. We don't get it proper, but we get a lot of it out. It is in a much better condition than when we started. And we're going to see that saturation come up. That superheat's going to start to come up. That discharge superheat's going to start to come up as well. Our supply air is going to start to come back up a little bit. Remember, we moved to high speed. We may need to go back to medium speed for humidity control. This space may not run well on high speed because of humidity. So you remember to put that fan back where we had it. Undo the things you did that were unnecessary. Put them back the way they were, unless you have a really good reason not to. And then we're also going to see that external static can come back down. Let's say after we're done at that 0.6, it's still high, but we're not freezing at this state. They can run for an entire day to let that space try to stay cool and not have to worry about it constantly icing over. It's still not going to run efficiently, but it'll run better. Yeah, and then we reschedule for a coil cleaning. And that's this scenario. Yeah, hope that was a good one. I feel like I get really kind of jumbled sometimes, and I just get to talking fast. Like after I see you. Oh, what the homeowner told you is that she just changes the filters, and you find a 5-month-old one in the trash outside, wet and gross. Yeah, yeah, true. Yeah, they before you get there, they changed the filter out, and they hadn't touched it in months. Yeah, yeah. What is your preferred manometer to measure static pressure? Mine seems to be drifting. I've had good results with the field piece manometer head. I still use that on occasion. Honestly, I think whether you go with Testo, field pieces, um, there's a couple of them out there. There's the Control Supply House will carry some. I don't think any of them is super crazy better than the rest, my opinion. Some of them you can buy really expensive ones, and those will probably hold up longer, hold up better. They'll hold a better calibration, possibly. But either way, with the way manometers are, you're constantly having to recalibrate them anyway. And if you're seeing them drift, I would question, just not to be insulting, but are you doing routine calibrations with your manometers? So you have to calibrate them in the space you're in whenever you go to hook up. So that way, um, you get a more accurate reading, and the building pressure and ambient pressures and whatever pressures are happening aren't influencing whatever that meter is doing. But yeah, any $100, $200 manometer, if it's not around $100, I think some of them are like between 80 to 100. if it's not at least $100, uh, I would really question the quality of that particular one. Thank you for examples. Yeah. Well, that's part of my goal here is I want this to not be over anybody's head. I'm trying to give you more advanced scenarios, but break them down to where we can talk through them. And it's where, we, as the experienced guys who can help talk through this, can jump in here and they get to helping engage in the chat. And I want you to be able to see what's our thought process, what's our mindset, how do we work through a situation like this, and not just have to um, rely on I guess just I don't know. I don't know where I was going with that, but yeah, just how can you work through this yourself to see this through? Anyway, I gotta go. I got a meeting to be at. I'm already late. Sorry guys. I'm coming. I'll see you there. Everybody have a good one. We'll see you on the next training.